Is Sir Darius here? Not. Jasmine Davis? Okay, which one? Okay. I'm trying to learn names and faces still because I only see you once a week, and it's so easy to forget. Oh, boy. I've written over your name so many times because I misspelled it. Miss Hawkins. Is she here? Oh, okay. I won't bother on the name. Brittany Alexandria Holston, not here. Trent, not here. Amanda Jones, not here. Felister, which one? That one. Okay, good. You were one of the new ones last week. Okay. Latandria, got it, thank you. Jasmine Mason, good, thank you. Kalisha? No. Oh, that's you. Okay, got it. Thanks. Vante? Not here. And Janice, right here. Okay. 1, 2, 3, 4, 5, 6. 3, 6. Evenly split. Okay. So number one was always remind to make sure I am recording, which I am now. You can tell by the little circle with 2 vertical lines. That means we're recording. We're on page 202, chapter 8, page 202. And the slide, again, presentation for this chapter is, and most of the chapters, really, really pathetic, okay? So I'll do most of them on white pages. Now, is anyone here who did not get a test last time? Okay. Let me get, yeah. I go right with the book, and I try to keep up with the slides with the book. Anyone else? All the rest of you got it. Now on this, you'll notice there's one correction made on number 7. A small railroad engine is able to exert a 175,000-pound pulling force. The 17,500 that was there won't work in this problem, okay? And I worked it out and found out it just will not work, but they just left off a 0 and put the comma in the wrong place. If you put that in, it gives you the correct answer. So it would not work without it. So that's why that correction was made. Now, what was your question? Did I answer it? About? Okay. Yeah, okay, I want to make sure. Huh? Oh, the book far better. Yeah. Okay, I thought you meant did I follow it? Okay.
Paying attention.
Yeah.
I know how to do it looking at my notes, but I don't know.
Right. Okay. Oh, for sure. The slides are so few and far between, so I'm writing as much as I can on the blank slides. But you know, even those get a little testy sometimes. Okay, where we left off before, we just introduced the concept of work. Now, any other questions before we get going today? Okay. Just introduce the concept of work, and the simplest definition of work, let me get my pen set up, is work is equal to some force, which we did in chapter 5, times the displacement. Now, the book uses an S there rather than D. I like D better, but I'll use what the book has, S. You can name it anything you want to, but the book uses S.
I think there's something else that confused me on the test, because like in our notes we got FN on the test.
Well, there's lots of different forces. Newton's second law is net force. Now, I usually use F sub n for that when that's appropriate. The book will sometimes just put F, and you don't know what force they're talking about. So I like to do Fn. But a problem comes because when they talk about a normal force, which is never a net force, but a normal force, they use Fn for that. So when you're talking about a component force, that's Fn. The total forces you could put F sub t, but then the book doesn't use F sub t either, so it's kind of a guess on what the book is going to wind up using. Can I get your name, please? Okay. Sir Darius, right? Okay. All right. Did you get the first test? Okay. Again, the first test, number 7, that's 175,000 pounds rather than 70,000 pounds. This will be today? No, it's you technically do a week from today, but if you need an extra week, you can have it. And I always like to give you a chance to ask questions, and since we only meet once a week, try to get it in. But, definitely before I give out the Chapter 8 test, try to get that one in, okay? And that'll be a little ways off, but this is a pretty quick chapter, I think. Okay. Now, was there another question? Okay. So this is a definition for work. Now, just reminding you of this, when you write this, work equal force times the displacement, okay, the magnitude of the displacement, that's if and only if the force is in the same direction of the displacement, okay? If I pull the desk straight out, then I displace the desk, the amount of my pull times that displacement, that is the work I did on the desk. Now I can pull with the same force perpendicular to that, and I'm trying to do it exactly the same force, and I'm not moving it at all. Certainly not in that direction. And even if it went in that direction, this force, is not doing any work on it. It can't, because they're in opposite or different directions. Okay, so force times displacement that way. So that is a sort of the caveat here. The force has to be in the same direction of the displacement. Now here's a sort of bizarre example of this, but it is a real one. This Earth, of course, moves around the sun, right? Now the gravitational force of the sun is pulling the Earth toward the sun. But because the velocity of the Earth is perpendicular to that, this force of gravity that the sun is pulling on the Earth is not doing any work on the Earth. It's changing the direction of our orbit, and you might think that's work. No, it isn't, because that's perpendicular. That's a perpendicular force to the displacement. It has to be in the same direction. Okay. Now, I can easily imagine this. You sometime or another in your lifetime have pulled, say, a kid in a wagon, right? Okay. So if you're pulling the kid in the wagon's down here, and you're up here, and the angle of the bale, I guess you call it, of the wagon is about like that, right? Well, you're doing a force, your displacement is in parallel to the ground, so only the component of the force, remember force is a vector quantity, has magnitude and direction. Since you're pulling this way on the bale, only the component of force that's in this direction is doing work on the wagon. The component this way is not doing any work on the wagon. It's moving it up, but it's not lifting it off the ground. Now, if it was lifting off the ground, that would be doing work. But it's not. The wagon is staying on the ground, so it's only the component in the direction of the displacement that does work. Okay. I gave the example last time, digging in the backyard, trying to move a rock, and as long as I did not move the rock, I was doing no work, even though I was grunting, pushing, shoveling, exerting all kinds of forces, but without moving the rock, I was doing no work. Okay? Tell me back then I wasn't working, I would have probably hit you with the shovel. No, I wouldn't have, but it's I was doing no physics type work on that object. Okay, the rock. Now, that's the bottom of page 202. Top of page 203, let's look at the units. Does anyone recall what the unit of force was? Either. We used two major units of force. Give me either one of them. Yeah. Say again?
Are you talking about the kilograms?
Yeah. Okay. Okay. Force is not kilogram, but it would be a kilogram meter per second squared. That is a unit of force. It has a name. Do you remember? A Newton. That's a Newton. What is the unit for displacement? Second? No, slug is the mass unit for mass in the U.S. customary. Displacement. How far something moved? Meter. So this would be a meter. Okay? Now, a kilogram meter per second squared times a meter would be a kilogram meter squared per second squared. This is a work unit. This is the force unit. This is the work unit. Okay? And that would be a Newton meter. And a Newton meter has its own name. Anyone know what that one is? Women's best friend. A joule. Okay. But it's not spelled like a joule. It's spelled Joule, but it's pronounced joule. Joule. Named after James Prescott Joule, and he has a little blurb in the top corner of page 203. And therefore, since it's named after a person, we use a capital letter for the name. Notice Newton is named after Sir Isaac, so we use capital N there. Meter is just named after the French word for to measure, metre. So that is not capitalized. Joule, however, is capitalized because the J is capitalized. That's a unit for work. Now, it doesn't seem like there's a lot of difference between a force and work, but there is. There's a couple. Number one, got distance, multiplied by. But number two, force, like I said, is a vector quantity, whereas work is not a vector quantity. It's what we call a scalar quantity. Magnitude only. There is no direction associated with work. You're either doing work or you're not doing work, okay? It doesn't have a direction associated with it, whereas force is a directional quantity. Now, how about U.S. customary unit? What was the unit for force in U.S. customary system? Now, SI was Newton meter, that's a joule. How about in the U.S. customary? What is a unit of force? Feet is the distance. What is the force measurement? Pound. Perfect. Pound. So usually we turn them around and call them foot-pounds. Okay. That is a unit for work in the U.S. customary system. So many foot-pounds of work. Again, force is a directional quantity, displacement is a directional quantity, but the product of them is not. It's a scalar quantity, magnitude only. Now, I kind of doubt the answer, any of you will have done this, but have any of you ever used a wrench, special kind of wrench that is measured, calibrated in foot-pounds? Probably not. I thought maybe Sir Darius, but probably not. Okay? A torque wrench measures in foot-pounds. Is that work? No. Torque is a vector quantity. In work, the force and the displacement have to be in the same direction, and that's... No, that's a ratchet. Okay, well, I know what you're talking about there. Now, you could have a torque wrench that does also ratchet, possibly, but what a torque wrench is when they're tightening the lugs on your car, they have to tighten them to a certain torque, so many foot-pounds. But that is there. Have any of you ever heard of a cheater bar? You haven't? Okay. I used them when I was trying to get that rock up, okay? Because what you do there, you put the fulcrum underneath there, and I've had a, say my pick. I had the point of it underneath there, and the handle was up here. Pulling like this, my force was in this direction, the displacement was in that direction. They're perpendicular to each other. That produces a twisting force, which is called torque. It's also measured in foot-pounds. Foot, pound. Pounds of force, pounds the distance from the center. But they're perpendicular to each other, and therefore, so what you do, if you have a long pipe and put the pipe down the handle there, pull like this, you get a lot more torque out of it because you have a lot more distance for the same force, so your torque is even greater. Now this is a twisting force, okay? I don't know if any of you have noticed this. Look under the hood of your car when someone is revving the engine, and that engine will sort of do this kind of motion. That's torque. It's perpendicular to the turning of the thing, and it actually will try to, if it wasn't for those motor mounts in there, it would fly out of the hood of the car. And if they ever broke, it does fly out of the hood of the car and bust your hood. So that's a different, that is a torque, but they're both measured in foot-pounds. So you just have to keep those separate, okay? I don't know what they called torque in the SI system. They probably just call it Newton meters, but that's not the same as a joule if you're dealing with, and here's the difference in those. And you don't need to know this, but I'm just telling you why there is a difference. Remember, force and displacement are both vector quantities. There's two ways that you can multiply vectors. One is called a dot product, and that produces a scalar quantity. The other is called a cross product, and that's called a vector product, okay? You produce a vector. This is what produces torque, and torque is also a vector quantity. Both of those are vectors, so the cross product does that. It's a different way of multiplying vectors. You don't need to know that, but I'm just telling you that's why there's two different foot-pounds. One's a scalar, one's a vector. The scalar are when the force is in the same direction of the displacement. The torque is when it's in perpendicular to the displacement. Okay. All right. A little bit more than you really needed there, but just in case you run across that. So here we have example 1. No figure on the slide set, so I'll try to do it, but I'll clear out my ink here so we can do it. Find the amount of work done by a worker picking up 225 newtons of bricks. 225 newtons of bricks. What's that a measure of? What do we measure in newtons? Second? Now, kilogram is a mass quantity. A newton is a kilogram meter per second squared. So a newton is it's kilogram meter per second squared. What are we measuring then? Remember our parameters? What was, when we were talking about work was what? What was the definition of it? Force times a displacement. Okay, what is 225 newtons? What's that? It's one of those three. No, work is measured in joules. Force is measured in newtons. This is your force measurement. Okay, now that has a special kind of force. There's many kinds of forces. When you say lifting 225 newtons of bricks, what do you reckon he's lifting? What would you call that? What would he call it? Boy, these are heavy. This is a weight force. This is your F sub W. The book doesn't put it in here, but that's the force we're talking about here, weight. And he lifts it to a height of 1.75 meters. So if this is the ground here, he's lifting up, and the height is 1.75 meters. What's that a measure of? The displacement, your distance. The book calls it S, to me, H is a better word for it, letter for it here, but we'll call it S just to keep up with the book. So guess what the work would be? There's the formula right there. 225 newtons times 1.75 meters. And that would be what? Someone got a calculator? 393.75. And what unit would that be? Newton meters would be okay, not newtons. You'd have to multiply units just like you multiply the numbers. But what is a Newton meter? A joule, exactly. Now, here's where we hit a little problem. It's not a problem, it's just an issue. This has how many significant digits? 3. This has how many significant digits? 3. So here you count off 3 digits. 1, 2, 3. Look to the right. Is that number 5 or greater or less than 5? It's greater. So we bump this up to make it 394 joules.
Okay, that was my question for one of the tests. When we look at those, we need to round it up by the numbers that's on there, like 3 numbers up.
Right.
Yeah,
Okay.
before you
Okay.
said you had a line over it.
Okay, that's if it's a 0.
That's if it's
Yeah, anytime you have a non-zero number, that's significant. It's only when you have zeros you don't know if they're significant or not, because they're not measuring anything. But a 0 with a line over it means that 0 is significant. And then also any number between a non-zero number and a 0 number, they have to be significant, because you count them all between those significant digits. Okay. So on that test question that we were talking about, number 7, since neither one of those zeros had a line over it, how many significant digits are we talking about? 175,000. 3 significant digits. Those last 3 zeros are not significant because there is no line over them. Okay? Now, after a decimal, it is like the 0.40 you see on the next line. That's the 0 in front isn't, because that's just a placeholder. The 0 after the 4 is, because that's 40 as opposed to 39 or 41. So that 0 is significant. Okay.
I guess that was my question for number 10. I guess I would need to round it up.
Okay, number 10, the 0 after the decimal is significant. So that has 3 significant digits, and the G is 1.63. That's 3 significant digits. So whatever your answer is, you should give the 3 significant digits.
Okay.
Now, I don't mark it wrong if you don't have the right number of significant digits, but I'll usually indicate what you need to do to it. I'll put okay. I'll give you credit for it, but always try to keep in mind you can't get more precision out of a problem than you put into it. So you couldn't get 5 digits out if you only put 3 digits in. Okay. Good. That was example 1. 394 joules. Or Newton meters would be fine too. Or joules, either one. Okay, now this time a worker pushes a 350-pound cart. This is example 2. So let me erase this. So he's pushing a 300 and do it this way. A cart which contains a whole bunch of bricks. Okay. Pushing a cart. Okay. Pushing the cart there. It's a 350-pound cart. Now, 350 pounds, what's that measuring? It has a whole bunch of bricks on it. No, 350 pounds. Pounds measures. That's a weight, which is a force. So 350 pounds is a weight, so that's the force due to gravity pulling downward. F sub W is equal to 350 pounds. Now, they don't put a bar over that, so we don't know it's just a two significant digit thing. He pushes a 350-pound cart a distance of 30 feet. Well, his distance, so on a flat level surface, that's going to be the distance, we'll call it S, is equal to 30 feet. That's your displacement. Now that does have a line over it, meaning two significant digits. The 3 is, and that. But he exerts a constant force. The force that he uses to push is 40 pounds. So I'm going to call it F sub P, his pushing force is 40 pounds. And that 0 is significant. Okay? Now, the question is, how much work does the person do? So what is the work? Force times displacement. But which force are we talking about? The push, because this is perpendicular to that. That doesn't do any work. Okay? It's the force of the push in the same direction of the displacement that you do. So this would be 40 pounds of force times 30 feet of displacement. And what would that be? 1,200, what unit? Second? Not? Okay, no, you multiply the units together just like you did. Okay, foot-pounds. Okay, we talked about foot-pounds. These are foot-pounds. You can put a dash in between them so you can do it. Now, do we put a bar over either of those zeros? No, because these are your two significant digits, that's all. But it's 1,200 foot-pounds of work. That's how much work he did. That 350 pounds of weight does not enter this problem at all. Okay? No, you just have to keep them straight. Work is force times the direction in the same direction. The force in the same direction of the displacement. You have to remember that. The force downward, the weight, no, doesn't enter the picture here. Okay, let's see how the book did. 1,200 foot-pounds, good for them. All right. Now it says, note in this example, the cart weight is 340 pounds, but the force that he has to push is 350 pounds, but the force he pushes is 40 pounds. Okay, now, here's why this did not enter the picture. Because if the earth is pulling down on that cart with 350 pounds of force, guess what? The ground is pushing up on the wheels with the normal force, which is the same magnitude. The total of that up is 350 pounds. So that is no net force. No net force, because the same weight down is the ground pushing upward. So that's why that didn't enter the picture at all. Okay. 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 Here's the deal. As you notice, the title of this chapter is Work and Energy. Right. Okay. Now, energy relates to ultrasound, how much energy those waves have. Okay. So you have to understand energy, but you can't understand energy without work, because those are two sides of the same coin. So you have to know that. So basically these first two chapters, and maybe even the next one, is basically giving you the foundation, the framework that your units, what you're measuring, all that is based on. If you don't know that, you can't make any sense out of the sound energy. So that's what we're doing, is laying we're using those bricks to lay the foundation. You're going to build the house on top of that, but you got to have the foundation. Yeah. Yeah. Now that's my interpretation of why you have to do it. But the thing is, the course description that the state came out with said you will teach force, work, and energy, blah blah, all these other things. in my mind, that's why you have to have it, because all the units and everything else depends on knowing where these things came from, what they are. All right. Now, for right now, we're going to get out of this and go to this one, okay? And we'll go from current slide. This is like the wagon I was talking about you're pulling. Sometime your force is not in the same direction of your displacement, okay? And if it's not, then you have to deal with the component of the force in that direction, okay? So this is your applied force, you pulling on the box, the wagon, whatever it happens to be, but since it's moving in this direction, now I've got to change my pen again, okay, then you have to concern yourself only with the X component, the horizontal component of your displacement, of your force, because that's the direction of your displacement. Your displacement is going to be in that direction, so is the, you have to concern yourself only with that component of the force. All right, someone slid on the ice playing in the snow, huh? No. Let's see. Would you be Trent? Okay. Still learning names and faces. My goodness, I think this is probably the most we've ever had in one single class. Great way to go, folks. Hope some more will come in. Did you get a copy of the first test? Okay. And on number 7, that was 175,000 pounds rather than 17,500. It doesn't work with the first number. So I made the correction there. Okay. Now, I know that the math requirement for this course did not include trigonometry, but you got to have just a little bit of it. So I'm going to, because your calculators all have these functions on them, this is just showing how you use them, okay? Now, here is the angle that your applied force, this is the rope that you're pulling this with, and you're pulling in this direction, so that's the force you're applied. But your motion is this way, so you're only concerned with the component of the force in that direction. The component up this way is doing no work because it's perpendicular to the motion, doing no work at all. This one is parallel to the motion, that's the component doing work. Okay? Now, here is the little thing that might help you with this. Some people like this one. Actually, a student just told me he had it. So, ka, toa. Now, to me, that means almost nothing. Okay? Well, it means something. I know what it means, but that's not the way I remember it. But a student once told me this one. Some old hen caught another hen taking oats away. Now that's just a little saying that to me would be helpful. I learned it just, and here's what I'm getting at. If you have an angle here, this is called the right angle, okay? That's the biggest angle in that triangle. This angle and that angle are less than that one. So the side opposite that is called the hypotenuse. Have y'all heard of that before? This would be called the adjacent side. This is the opposite side, because here's the angle. The angle adjacent to that is the adjacent side. I mean, the side adjacent to the angle. The side opposite the angle, that's called the opposite side. So sine of theta is the opposite side over the hypotenuse, that over that. We're not interested in the opposite side here. That's the one that's doing no work. The one we're interested in is the cosine, because the cosine of that angle theta is the adjacent side over the hypotenuse. That's caught another hen. You see it? So that's the one. This over this is equal to the cosine. The adjacent side over the hypotenuse is the cosine of that angle. And then for future reference, taking oats away is the tangent of that angle that we're not going to be using now. I don't think we will, but tangent of that angle theta is opposite over adjacent, this over that, which we're not using in this case. All we're using here is the cosine. And the reason we use the cosine, that's the adjacent side over the hypotenuse. Okay? So, if we're interested in getting this, we know how much force we're pulling with. We got a scale up there pulling, you know, a fish scale or something else like that, that measures how many pounds of force. That's on the rope like this. We want this one. If we somehow know this angle that we're pulling between the horizontal and the direction we're actually pulling, then this is what we're looking for, the adjacent side, which in this case is Fx. So Fx is equal to the applied force F, which is the hypotenuse here, times the cosine of the angle theta. That's why we use that formula, because this is caught another hen. This is COH. This is the hypotenuse, and if you divide both sides by that, the cosine is the opposite over, adjacent over the hypotenuse. Caught another hen. That's this one right here. So that's all you have to remember. If you have an angle, use the cosine, because that gives you the adjacent, and that's the one we're looking for. Okay? Now, on your calculator, I think all of you have calculators or telephones that have sines and cosines on them. The only one you're going to be using for this is the cosine. I don't think there are plenty of other places in physics you'll use sines and tangents. This is not. This is where you use this. So let's do example 3. I believe that comes with a figure. Yes, this is it. A person pulls a sled along level ground a distance of 15 meters by exerting a constant force of 215 newtons at an angle of 30 degrees with the ground. How much work does she do? Okay. Poor gal, they're making her do all this work. So here is the 215 newtons of force. She's pulling on the cord, so that is at that angle. The sled is moving in this direction. There is the displacement. How far is that displacement? A distance of, you got your book, example 3, distance of 15.0 meters. That's the displacement in this direction, okay, along the ground. The force is up this way. Well, not all that force is pulling the sled. Only this component of the force, that's your, what I call the horizontal component. I think the book called it F sub x, but I like F sub h because that's the horizontal. But F sub x is fine too if you prefer that. This component this way, doing no work at all. That's the opposite side. So, using the formula we just had, oh, I didn't actually write that formula down, did I? Let's write it down here. Work here is equal to the force. Now that's the total force that you measure times the displacement. However, that's not in the same direction, so then you have to multiply by the cosine of the angle theta right there. So that's where that comes into play. Now let me tell you this about sines and cosines. They're always, always, always between -1 and 1. We're only going to be between 0 and 1. So they're always less than 1. So this is always going to be something less than the applied force. If you ever get it more than applied force, you've just created some force there. You can't do that. It's always less than the applied force because the cosine is always less than 1. Okay, so let's come over here to this example. What would be your formula for calculating this? What work does she do? Work is equal to, what did I just give you? Force. Displacement. But because these are not in the same direction, we have to multiply by the cosine of the angle theta. And the angle theta here is 30 degrees. Okay? So if you got a calculator, get used to it. Now, with your calculators, let me tell you this.
Yeah, that's what I'm looking at. Mine's not coming up with this.
Okay, and here's why, I bet you. Okay, you've got a scientific calculator, is that right? Okay, does it have a little DEG written somewhere on that display, or does it have a RAD? Okay. Hold it slow. I'll move that slow here. All right, it says DEG, and that means degree. Now, some of you may have calculators or your phones. You have to know which mode you're in. Since this angle is given in degrees, you'd be in the DEG mode, which you are in. If you don't have that little showing on your calculator, you need to find out what mode your calculator's in first. You are going to generally stay in degree mode. Okay? Radian is a totally different measurement. It's measuring the same angle, but it gives it a different number. That would be, by the way, 30 degrees would be pi sixth, which is 1/6 of pi, which is 3 divided by 6. It's a little over 1/2, 0.5. Okay, you want 30. Okay, so here's what you do. It's force, 215 newtons, times displacement, 15 meters, times, now, depending on your calculator,
because I think it's going to be like a different number from the book when I put it in.
okay, let me watch you put it in.
So, 215 times 15.0.
No, you don't need 0.0 there, just at the end.
And then the
Times.
and cosine,
Right.
which is 30.
Right.
Leave 0.
Yeah. Yeah, you don't need the 0.0. Yeah, close parentheses.
And it's giving me 279.
What did they get?
279.
Okay.
37.90.
Okay. Okay. I thought you meant it was a big difference.
Not too much.
Did everybody get some answer? Okay. Read me the answer you got.
2,792.
Okay. 2,792.9. What unit would that be? By the way, cosine has no units at all. So that would be force in newtons multiplied by displacement in meters. A newton meter is the same as a joule. Okay. Now is when we look at our significant digits. 3 significant digits there. 3 significant digits there. You start here, count 1, 2, 3, look to the right. That's less than 5, right? So you drop that one. It's 2790 joules. That's why they gave you that answer. I thought you meant it was a big difference.
No.
Okay. Okay. Now, again, yuck. Again, if this was a test question and you put 2792 or even round that up to 2793, I'll just indicate that you rounded badly, but I don't take off points for it. Okay? The deal is you can't get more precision out than you put in. Okay? That's a physics thing. I don't know if sonographers really are going to care much about that, but in physics you do tend to care about it. This would be indicating you had more precision coming out than you had going in. You can't do that. Okay. Did everybody get that or something close to it? Okay. You see how your calculators work? Be sure you're not in RAD mode, radian mode. You will not get anywhere close to the right answer then, I guarantee. Okay. Now, you could have left that as Newton meters, or you could have written it as joules. Okay? The next one I don't think we have a slide on, so what I'm going to do is go back to the other slide. Okay, and that means I have to get my pen back. Okay. Juan and Sonja use a push mower to mow a lawn. Juan, who is taller, pushes at a constant force of 33.1 newtons. So here's Juan. My stick figures are terribly ugly. Okay. Okay, it's not that funny. Okay. Here's my stick man. Okay. He's tall and he's pushing. No, he's pushing down on the mower here. So let me correct that. Y'all all mowed, you know how this goes. Pushing down toward the mower with a force of, I just read it and I can't remember, 33.1 newtons. So this is a force applied. I'm going to put sub A. 33.1 newtons. Okay? On the handle, and the handle has an angle of 55 degrees with the horizontal. So this is 55 degrees here. That's the theta for 1. Okay, this is 1 here. Okay, J-U-A-N. All right. 55.0 degrees. I left off my significance there. All right, I erased too much. 55.0 degrees and 33.1 newtons, 3 significant digits in both places. Okay, Sonia, who is a little bit shorter than Juan, why she'd be wearing a dress out there mowing the yard, I don't know, but so you can tell it. This is Sonia, who is shorter, pushes a constant force of 23.2 newtons. So she's pushing downward like this, and that force downward is force due to Sonia. I better put this for 1. Okay, force for Sonia is only 23.2 newtons. Second, at an angle of 35 degrees. So this angle is much because she's shorter, 35.0 degrees. Okay, that is theta sub Sonia. Okay, with the ground. Assume they each push the mower 3,000 meters. So I'm not drawing the motors here, but mower here, but he goes 3,000 meters. Only the second zero, the middle zero is significant, which means all 3 of those are. This one is not significant. She also goes 3,000 meters. That is your displacement, S. Okay? Who does more work? And by how much? Just looking at that, big old tall Juan pushing with a force of 33. Say again? How'd you get it? Okay, except they're doing different forces. And work is force times displacement. But you'll be surprised how close to the right answer you are, okay? Because the force is, the work done by 1 is force by 1 times displacement by 1. I keep putting D they use S. And you're right, they do the same displacement. S for 1. But what else do you take into account? This force is downward. The mower is going that way. You have to take the horizontal component of that force, not the total force. I like to call it F sub H. They call it F sub X, which is fine. What will that be? Has to do with that angle. The cosine of theta 1. Okay? Whereas work done by Sonia is the force done by Sonia times the displacement by Sonia, SS, times the cosine of the angle for Sonia. Okay? Well, Juan's force was 33.1 newtons, and he pushed it 300 meters, 3,000 meters. But his cosine was of what angle? 55.0 degrees. Whereas Sonia pushed with only 23.2 newtons of force, and her displacement was also 3,000 meters, and times the cosine of her angle, which was only 35.0 degrees. Okay? Punch them in, see what you get. Awfully close, isn't it? The same, okay. What number did you get? Oh, I see.
So I'm following along.
Oh, I got 56, 956.
56956. Okay. And that would be what unit? Joules. And how about Sonia? Say again? I can't hear. Yeah, Joule is the unit, but how about Sonia? Punch her numbers in. Okay. 0 what? 12.9 joules. And that would be Sonia's work. So it looks like she might be doing a little more work because her angle is less. However, how many units we have here? 3, 3, 3, 3, 3, 3. So you go 1, 2, 3, look to the right, and what do you get? 5 or more, so you bump this up 1, 50. If you bump that 9 up, it becomes a 10, so that becomes 670, 57,000 joules. And hers, 1, 2, 3, look to the right, that's 1, so hers is 57,000 joules. Now, on both of these, you put a bar over that first 0 there, because that one is significant. Okay? Now, so for significant digits, they did the same amount of work. Not taking into account, she just does a little bit more, but it's not really significant more. Okay? So they basically do the same work. You were right in your guess, but for the wrong reason. Yeah, they did the same distance, but they exerted different forces. But they're components of the force, because his was 55 degrees, hers was 35, that cosine theta evened it all out. All right. Good deal. And in the book, you got, 57,000 joules for both. Even though I don't like this. It says, however, one must exert more energy because he pushes into the ground more than Sonia. Wait a minute. Exerts more energy. I guess that is sort of right, because if you were to look at the wheel tracks, because he's pushing down at a greater thing, he's compressing the soil a little bit more than she is. See, to do more energy, you have to do more work, and he does some work against the soil. So that's a real stretch there, but it is true that he does push down more than she does. And in another sense, it's even more complicated than that, because the more he pushes down, the greater the normal force, and there's got to be friction. And friction depends on the normal force. Didn't we do that in chapter 5? So there's more normal force, so he's doing more work against the normal force than she is. Okay. Interesting problem. Number 5, example 5. All right, to erase this. Everybody got it? Okay. Find the amount of work done in vertically lifting a steel beam with a mass of 750 kilograms. So here's going to be this steel beam. Now, I don't draw steel beams well, but I'll try to get this one. Okay, something like that. That's an ugly beam. Okay. Vertically lifting, so here you've got something tied around each end, and you're lifting this upward. And its mass, the mass of this steel beam, mass of the beam is 750 kilograms. That's pretty massive. Steel beams weigh a lot, okay, but that's not a weight, it's a mass. At uniform speed, a distance of 45 meters. So he's going from here to there. That's a distance of 45 meters. Notice here there's no bar over. Hey, I'm sorry? Oh, absolutely. Just right there to the right. I mean, right down the hall. Okay. Notice there's no bar over that 0, so you only got 2 significant digits there, and there's no 0.0 here, so you got only 2 significant digits there. Okay? Now, find the amount of work done in vertically lifting a steel beam with a mass of that, uniform speed of that. So how do we get work? Force times displacement. And here, there's no angle. You're lifting upward, and the beam's moving upward. So you don't have a cosine theta to worry with. Oh, shucks, okay? We love our cosine thetas, don't we? Okay? Now, do we have a force, though?
You get put down the same force. So what you feel in the work and the...
Work is force times displacement. I have a displacement here. This is my S. Okay. What is this? That's what? That's mass. So do we have a force? How? This is why we had to do chapter 5 first. What did we learn on 5?
Mass equals...
Say that the wrong way. The force due to weight is the... Oh, how soon we forget. Mass times acceleration due to gravity. Because it's gravity. That's the force we're working against. Yes, okay. So mass was 750 kilograms. What's the acceleration due to gravity in the SI unit?
Is it the 9.8?
9.8. You could put a 0.0 if you wanted to, but you only have two significant digits there, so it doesn't even matter. Meters per second squared. That's an acceleration. Meters, distance per time per time. So you have to first do this, and what does that give you? 7,400 and something.
7,350.
Say, oh, 350? 7,350 what?
Kilograms per meter squared.
Okay, kilogram meter per second squared,
Yeah.
which is also a what?
Newton.
That's also a Newton. Perfect. So you have a force of 7,350, my screen is sinking on me, newtons, multiplied by what is your displacement or your distance? 45 meters. And that would be goodness, something around 15,000. No, more than that. No, 50. Yeah, maybe more like 17,000. Wait, it's halfway between. No, way more than that.
Yeah, I'm trying to figure it out myself. Hold on.
330.
Yeah, that sounds reasonable. Say again, 300 and, really, that much? 330? Or is it 33,000?
0.075.
No, you're right. 33,000 what? 750 what unit? Joules. Okay. Now, but, wait. Notice here, two digits. So, well, they should really round to 34,000. Okay, which is okay too. You're just multiplying, so that's all right. I need to see that on a calculator. Well, wait, I've got one. I'm going to have to lose this though to do it. So if you do it the way they did, 750 times 9.8 times 45.
That's how I got my answer.
And what do you get?
3,000.
Okay, yeah, I'm sorry. Okay, wait. Wait. I didn't put enough digits in there. Yeah. Okay. I heard you saying I wrote it down wrong. Okay. You said
330,700.
that makes sense. Okay. And that would be joules. Okay. Well, how many digits? Two. This one had 3, but you can't get any better than your least. Go 2 digits, and guess what? Look to the right. That's a 0. You're not going to add any more to it. So that'd be 330,000 joules. Or they write it in scientific notation, which is 3.3. Now they moved the decimal from way over here. 1, 2, 3, 4. Wait. 1, 2, 3, 4, 5 places times 10 to the 5th joules. So that's how they got that answer.
Yeah, they get some extra steps.
Yeah.
I guess to keep you from writing all those out.
Yeah, that's it. When the typesetter was lazy and didn't want to type all those units in, so all those zeros in. So they just put 3.3 times 10 to the 5th. That's how many places you move the decimal in for 330,000. There's 3 to get the thousands, and then 332 more. So 3.3 times 10 to the 5th joules. Perfect. Okay. Now, they ask a question there. Since this was one of our answers, 330,000 joules. Another way to do it, what is the prefix that means 1,000? Second? K, kilo. So you could say 330 kilojoules. That to me would be simpler than writing scientific notation or carrying all those zeros. Just knock off 3 zeros and make it kilojoules. And that's what they say here. Do you see that that would be an acceptable answer? Yes, we see that. All right, homework exercises then in 8.1. They left off the numbering for 3 and 5, okay? They have 1, 2, and then a problem with no number 4, and a problem with no number 6. So that, huh? They have 3 and 5 on that one?
No, I said they had fun with it.
Oh, yeah, they did. I don't. And this is the 11th edition, and that they haven't caught all these mistakes. It just doesn't make sense. But anyway, they may have put new problems in, forgot to put the numbers in. I don't know. Do any of the odds 1 through 5. Then do any of the odds 7 through 13. Or, let's just say, whoa, there's so many of them there. And then any of the odds 15 through 23. Okay. All those are ways to do that. All right. Now let's see. I can't recall what. Oh no, yeah, I do recall. The next PowerPoint slide is another section or two away. Yeah, it's way back in 8.4. We're not there yet. What's that? I can't hear. Oh, okay. All right, so that finishes 8.1. All ready to go 8.2? 8.2 is now going to be talking about power. Okay, so I'm going to erase this if it's okay. All right. Now,
Let me just get a picture at the time that I need to catch up on.
oh, okay.
Oh, you're
Yeah.
recording.
Yeah. Okay. 8.2 is talking about power. So how does power relate to work or energy and time? I'm going to take you back just a little ways, not too far, but just a little ways. Remember when we first started talking about a displacement, a distance, okay? And then we said once we had that down, if we measured how long it took us to do that, we could talk about a new quantity, the time rate of change of displacement, which is our speed or our velocity. Well, when we got that one down, what if that were changing? Well, the time rate of change of velocity is acceleration. So quite often in physics, once we get a quantity and we got used to it, let's take the time rate of change and see what that tells us. And we get new units. Well, I think if you recall, the time rate of change, no, we didn't talk about momentum. But if we had, the time rate of change of momentum is force, okay? Well, here we talked about work, and later we'll find out energy is the same type thing. Well, let's take the time rate of change of work, or time rate of change of energy, and that's what power is. Power is work divided by time. The time rate of change of doing work. Okay? Now, for those who weren't here last time, you'll hear this story for the first time, but those who were, this picks up from where I talked about last time. Remember last time I talked about digging out our patio in the backyard? Anyone here to remember that? Okay. And we talked about whether I did work on the rock or not. And unfortunately, you told me I didn't do any work on the rock until it moved it, you know. So all that running and effort and sweating and everything else, doing no work until I moved the rock. Okay. Well, I worked, if you remember the story, I had mini-term class. We were on quarter system then. 5 weeks, the first 5 weeks of the summer, then the next 5 weeks I had off. So for that 5 weeks, most of that 5 weeks, just about every day, not every day, I did always work on Sundays, and occasionally we had to do some other things, but generally most of the 6 days a week, for those 5 weeks, I was out there digging on that patio. And occasionally my wife came out and helped a little bit. She would run the rototiller, and I would shovel and stuff like that. But anyway, we worked on that, and about 5 or 6 weeks in of working like that, we still had only dug about half of the patio out. Because, I mean, some places it was really deep, you know, maybe this high. You were digging that much with rocks and everything else in there, and having to haul this soil away. And we're going to start back fall term. It was the right after Labor Day weekend. So there's no way I was going to finish the patio because 5 or 6 weeks were gone, and I only got about half of it dug out. But by that time, I had made a big enough space you could get a bobcat in there. Before that, there was just no room to maneuver, because there was a house here, there was trees here, there was a hill here, there were plants here. There was no room. You had to do it by hand almost. But by this time, I had covered enough area you could get a bobcat in. So we called around that Labor Day weekend, and sure enough, found a guy that would come out with his bobcat and dig out the rest of that patio, which he did in an afternoon. Now, I got half of it dug, but it took me 5 weeks. He did the other half in 5 hours. What was the difference in that? We did the same amount of work, approximately anyway. I did half of it, he did half of it. But what was the difference? That time. And power is work divided by time. I guarantee that bobcat had a lot more power than I did. That bobcat, my guess, was probably 250, 300 horsepower. Me, way less than half a horsepower. Probably a third of a horsepower, especially on a long day. By the end of the day, not doing very well at all, okay? That's the difference, the power. We did the same amount of work, but he took a lot less time, which gave him a lot more power. I took more time, which decreased my power. That's what power is, work divided by time. So we need some units for that. What are the units for work? Well, how do we define work? Force times a displacement divided by time. And what's the units for force? Okay, a kilogram meter per second squared, which is a Newton. Displacement is meter, and time is in seconds. Okay, so a Newton meter is also a joule per second, and a joule per second is a watt. What? A watt. No, never mind. A watt. Okay. What? Watt. Okay. All right. That's a capitalized watt too. Wonder why? Named after James Watt, who was the Scottish engineer, scientist, who did the first measurements of power. He was also largely involved with developing a steam engine, and he was wanting to know how this compared with the work that a horse could do, so he compared it to horsepower. And he's the one who defined that term, horsepower. Okay. Now, Back then they were using pounds and other things like this. So this unit in the in James Watt, there's a little blurb on him at the side of page 208, and I'll give you the unit here. The other unit for power would be work, which is force times displacement. In the SI unit, force would be pounds, displacement feet per second, foot-pounds per second. It doesn't have names for that. Now, you could leave it as foot-pounds per second, but what James Watt did is to find it this way. He said 550 foot-pounds per second is 1 horsepower. Okay, so that's where you got a horsepower. Okay, you could also multiply that by 60 and get 33,000 foot-pounds per minute, which you can multiply by 60 again to get foot-pounds per hour or so on. That's how much work a average dray horse could do in a day would be 1 horsepower. Okay, it's quite a bit of work because those are pretty big old horses. Okay, now power, just like work, is a scalar quantity. It has no unit, so it's not a vector. So there is a little activity here. How much equivalent horsepower do you possess? And it says if you walk or run up a flight of stairs, you can measure the horsepower you create. Well, the horizontal part you move doesn't contribute anything. You're working against your weight, which is downward due to gravity. So it's only the vertical distance you do. So if you measure the vertical distance between where you start and where you end, that times your weight, that will give you how much work you did in foot-pounds, right? Now, use a stopwatch to see how long it takes. And when you walk up the stairs, it's going to take longer than if you run up the stairs. And running up the stairs, you will probably do a pretty good fraction of a horsepower, okay? Walking up the stairs is probably going to be a pretty small fraction of a horsepower. But running, you could do more. But if you kept running up really tall stairs, like maybe Bryant-Denny Stadium or something like that, you're going to slow down before you get to the top, so your horsepower won't be nearly as much as 1 horsepower. It'll be considerably less. So let's go to example 1 on page 209. Keep in mind this formula. We will be using it. A freight elevator, this is an elevator that carries pretty large amounts of weight. A freight elevator with its operator weighs 5,000 newtons, with the middle zero significant. So that means all 3 of those digits are significant. This is the weight. So this is the force due to weight. That's what the book usually calls it. Except now it just uses F, force. I like to use subscript to remind myself what we're talking about. If it is raised a height of 15 meters, so this freight elevator is going to start down here and go up 15 meters. So that's going to be your displacement. And the weight is going to be, because you're moving straight up, the weight is down due to gravity pulling down on you. So that gives you your work. Force times displacement is work. Okay? But you know it takes 10.0 seconds, right? Yeah. So now we can calculate power. What is the power? Force times displacement
over
time, yeah, okay. And your force was 5,000
I'm sleepy.
newtons times your displacement, 15.0 meters, divided by 10.0 seconds. Okay? Now, 5 times 15 is 225, I think. Okay? So that would be 225 with 3 zeros divided by 10. So that's going to drop off a 0. So I think 22500, what unit? Newton meter per second. That would be a joule per second, which is a what unit? What? 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 Okay, never mind. I was trying to lead you into it. Okay, a watt. Power is measured in watts in the SI units, or horsepower in why I messed that up somehow.
Yeah, I think so.
I think my calculations are 5 times 15 is not 225. What is it? I was doing it in my head and it didn't work. Ooh, the eraser's not working.
75.
Oh, 5 times 50. Yeah, 5 times 5 is 25, times 3 is 75. Okay. 75,000 divided by 10 would be, let me erase that too, would be 7,500, right? Watts, which that 0 would be significant. Okay? Now, if you didn't like that big a number and want to go to a smaller number but a bigger unit, what would that be? What means 1,000? What? Kilowatt.
Yeah.
So 7.50 kilowatts. Okay. Kilowatts sound familiar?
Why do they have,
Newton meter per second.
right.
That's exactly what we're here. Newton meter per second.
Oh, okay.
But a Newton meter is a joule, and a joule per second is a watt.
So either way.
Either way.
Okay.
The units, as long as you got them right, you know, they're, yeah, even if you miss the units, I'll usually just correct them, but not count off anything. Okay. All right. Now, all right with that one? Let's move to example 2. All right to erase? Yeah. Okay. Example 2 here. Okay. I think I remember. The power expended in lifting a 825-pound girder. Okay, what's that a measure of?
Some of the pound.
Yeah, pounds measures. What does pound measure?
Is it
Second?
slug?
Second?
Slug?
No, okay. Slug is a unit that measures mass. So a pound can't be a slug because a pound measures weight and a slug measures mass. So that's not the same.
Pound.
That is a weight, which is a force due to weight.
Oh, okay.
Gravity's pulling down with that much force. Okay? To the top of a building 100 feet high. So here we have a building 100 feet high. Okay? And you have this girder that's being lifted from down here and lifted all the way up there and moved to the top of the building. So the weight of the girder, the force due to weight, is 825 pounds. You're lifting it 100 feet. And you said the power expended was 10 horsepower. The power is equal to 10.0 HP. That's not Hewlett-Packard, that's horsepower. Okay? And the question is, how much time is required? Time is the unknown here. That's what we're looking for. So what's our formula that we start with? Okay? The power is equal to force times displacement divided by time. Okay. Now, the force here is your 825. That would be pounds. Your displacement is 100 feet. Okay. Making fun of my writing, I can tell. Okay. And we don't know the time, but we do know the power. What was the power? 10.0 horsepower. Well, wait a minute. Our right-hand side is going to be in foot-pounds per second. Our left-hand side is horsepower. So we got to have a conversion in here. What is our conversion to get from horsepower to foot-pounds per second? Well, what we got to do is have our conversion here, and we match the numbers first. I mean the units first. Always put the units in their place. Well, this is foot-pounds per second here, so now I'm going to have to put it down here. Foot-pounds per second here to cancel out the foot-pounds per second here. I don't have the seconds in there, but it will. And that makes a horsepower. Well, what was the conversion? If you look up at either the bottom of the previous page, top of this page, you'll see what that conversion is. Actually, bottom of the previous page. In the little green block. Say again. 550 goes down here. 550 foot-pounds per second is 1 horsepower. Okay. Now, I put that all in there, but we really want to know time. So, probably I should have calculated the time first and then done the rest of it. So let's back up and do that. It's just a lot easier than carrying all those numbers around. Force times displacement divided by time. So to get time by itself, let's first multiply both sides of the equation by time, right? That'll wipe it out, because we don't like time being in the denominator. That's going to be a fraction. We don't like fractions, do we? Not very much. Okay. So, but what we got to do is divide by the power. Okay? Now here maybe is where we need to change our units. We have 10.0 horsepower. Okay? Let's multiply this by, now we're going to change it a little bit, and we want to get it into foot-pounds per second. Okay? Now these two blanks, the first blank is for numbers, the second blank is for units. Always put the units in the place. And this way, doing it this way, we want horsepower in the denominator so we can cancel it out. So that's going to put foot-pounds per second in the numerator. And we already knew from before that 550 foot-pounds per second is 1 horsepower. So multiply that by 10 and you get 5,500 foot-pounds per second. That's going to be the power we put here. Okay? So here's what we're going to do. Up here to this equation we got going here, that power times time is equal to force times distance, displacement. We're going to divide both sides by power. But this time we're going to be in foot-pounds per second, not horsepower. So the time is equal to force, 825 pounds. Ooh, my screen collapsed on me. Times displacement, 100 feet. That gives me foot-pounds. It's going to take, divided by power, and that is the one we got here, 5,500 foot-pounds per second. Okay? So here the feet are going to cancel out, the pounds are going to cancel out, the seconds in the denominator here, because it's in the denominator, flip over and go to the numerator, which is going to give us time in seconds, exactly like we want. So all that's left is doing the math. So multiplying 825 by 100 will be 82,500 divided by 5,500. And it's real easy to divide both of those by 100. So 825 divided by 55. What do you get? A little louder? 15?
You say 825 divided by 500?
Well, it's 825 divided by 55 or 82,500 divided by 5,500. 15. But we need 3 digits, so we put a 0.0 after it. And that will be seconds. So for that lift, to do that huge 825-pound girder up 100 feet, which is quite a ways, the motor is only rated for 100 horsepower. That's going to be 15 seconds. And that makes sense. That sounds pretty reasonable. What did they get in the book? 15.0 seconds. Why the 0.0? 3 digits here, 3 digits here. Oh, that 100. I didn't write it down. That had a bar over that. Okay, good. This had a decimal, so that was 3. And 550 horsepower. That's exact, so we know that 0 is good. They didn't specify that, but it is. That is good. 550 horsepower, foot-pounds per second makes 1 horsepower. Okay, 15.0 seconds. So quite often in a problem like this that has so many pieces to it, go on and solve for the variable you're looking for. Since we're looking for time, set up your formula this way, solve for the variable first, then plug in the numbers. It's just a lot easier than doing. Now remember too, on this one, we started off with foot-pounds and going to have time in it, but they gave us power and horsepower, so we had to use our conversion factor to get to foot-pounds per second, which we did. Yeah, that was one of the more multi-step problem. We'll put it that way. Okay. And they show here the conversion that we did. Only they did it a lot more complicated than we did, I think. But ours is complicated enough. Let's see if we can get example 3 done before we have to go. What you think? Anyone need this a little longer? Okay. So, example 3. The mass of a large steel wrecking ball is 2,000 kilograms. They told you that's the mass. 2,000 kilograms, with the middle 0 being significant. That means the first one is also significant. 200, those first 3 digits are significant. The last one's there, but it's not significant. Okay. What power, so we're looking for power this time, that's your unknown, is used to raise it, that steel wrecking ball, to a height of 40 meters if the work done is done in 20 seconds. So the S, which is your height, I like H better, but they use S, is equal to 40 meters. Okay, and the time that it took is 20 seconds. Okay. We're looking for power. What is power? Force times displacement over time. Okay? Except we don't have a force on here, do we? All we have is a mass. How do we get force? What's Newton's second law? F equal ma. Mass times acceleration. Only this time, since we're lifting it upward, what's our acceleration? Not just any old a, but one specific acceleration. What would that be? Acceleration due to gravity. That's called g, little g. Okay, so the mass is 2,000 kilograms. And what's our acceleration due to gravity? 9.80. What unit? Meters per second squared. That's the unit for acceleration. So that's what we're going to use for the force. So the power will be that force. I'm doing it like the book does this time. 2,000 kilograms times 9.8. Yuck. 0 meters per second squared times displacement, 40 meters, divided by the time in 20 seconds. This one we already knew what we were looking for, so we go for it. Now, if you use these basic units, you're probably going to come up with a unit you find rather strange. So what I would do, I would take these units and multiply those together, and what does that give you? Kilogram meter per second squared. Newton. Okay? And then times a meter meter is a joule. Okay? Now a joule per second is a what? A watt. Okay, yeah. Okay, so a joule per second is a watt. So we're going to wind up in watts, so don't have to worry with the units anymore. You know the answer is going to be in watts. So take the calculator and multiply these together. It's too late at night for me to try to do this. Oh, I will make it easy this way. 20 will go into 40 2 times. Okay, that will make it a lot easier. Okay, so 4,000, 2 times 2,000 is 4,000. And multiply that by 9.8, that's 39.2. It's 392. That's your numbers, and that would be 1 0 for that one, another 0 for that one. That's the metric prefix for 1,000. Okay, so this is 39,200 watts, which is, to get a smaller number, bigger unit, is 39.2 kilowatts. Remember, a meter is about this long, right? A kilometer is more like a mile. That would be 1,000 of these, right? So think of it that way. Kilo means 1,000. Kilometers, kilowatts, kilograms, kilo whatever means 1,000. Okay. I think we got time for another one, don't we? I think so.
I think I got time for questions to have.
Oh, you got questions? Oh, I'll stop and answer
not
questions.
From this chapter. I have a
Yeah.
question from chapter 5.
Okay, you want to do those next? Before
yeah,
you...
that'll probably be good.
Okay. All right, so what we'll do is pause here. Example 3 we did, so we'll start, unless we have time at the end of the questions to do example 4, but otherwise that's where we'll start. What are your questions from chapter 5?
With 5.4, I'm kind of, well, I wasn't here last class period, but I'm confused, kind of confused on
Okay. Well, that's why we have questions, to clear.
friction
5.4. Is that the one you're talking about?
Yeah, page 134.
134, getting closer. Okay. And which one? All right, to go to a clean page here. Everybody got this one? Everybody got it? Yay or nay? Got this? Oh, okay, good. All right. So this is page 134. This is problem set 5.4. And which number?
Number 5.
Number 5.
I'm actually kind of confused about the overall when they say the coefficient of friction.
Okay. Let's take a look and see what we got here. A dog sled weighing 750 pounds is pulled over level snow at a uniform speed by a dog team exerting a force of 60 pounds. Find the coefficient of friction. Okay. So what we have here is a dog sled. Boy, this is going to be ugly. Okay. Okay. Being pulled by a dog team, and there'll be all these little dogs running in here. Those are going to be little dogs. Okay. Now, the sled weighs weight, meaning force due to gravity, F sub W is equal to 750 pounds. Okay. Pulled over level snow, I tried to draw a level snow field there, at a uniform speed, meaning it's not accelerating, so that's, don't have to worry about that, by a dog team exerting a force of 60 pounds. So this whole team of dogs is pulling with a force, I'm going to call it the pulling force, of 50 pounds or 60 pounds? 60 pounds. I read it and I couldn't remember it that long. Okay. 60 pounds. And that's 0 is significant. Okay. Now, there's the force due to the weight, and that 0 is not significant. They don't have a line over it. So 2 significant digits here, 2 there. Okay. Now, if you look to your, basically the top of the page there, you'll see the working equation is the coefficient due to friction, that's your mu, is equal to the frictional force divided by the normal force. Okay? Now, here a little bit of, and this may be what you miss. Okay, the sled is not moving up or down, is it? Even though the weight's pulling downward. That means the ground or the snow is pushing upward with exactly the same force. This is called the normal force because it's perpendicular to the ground. And that is 750 pounds. Okay? Because it has to be. Since there's no motion up or down, it has to balance out and be no net force vertically. Okay. Now, the sled, the dogs are pulling with a force of 60 pounds that way, but it's not accelerating. So there's no acceleration here at all. So there's no, acceleration is 0. So the only thing they're pulling against is the frictional force. That's why they're having to pull with the power. And since there's no acceleration, the frictional force also has to be 60 pounds. If this were any greater than that, then they'd be accelerating. Since they're not accelerating, they have to equal. Okay? So now we have what we got. Frictional force is 60 pounds divided by the normal force, 750 pounds. The units go out, and the coefficient due to kinetic friction, because this is moving friction, is a dimensionless quantity. So get your calculators and see what 60 divided by 7. Actually, you can make it easier. Just do 6 divided by 75. Just divide both of those by 10. And you,
0.08.
okay, 0.08. Is that what you said? Okay, and that would be a dimensionless quantity. And that should be what the answer is. Did you check it in the back of the book? I have a mark somewhere back here, but I have so many marks back here, I don't know which is which.
So, number 5 is 0.080.
Okay, why that? Because these zeros are not significant, so you have to add one. Since you had 2 digits here, 2 digits here, you need to add one. So that is your...
Okay.
It's the same amount, it's just a more precise.
Yeah, I guess it's, with these questions that's on the test, I guess you gotta really read them really clearly to
Right.
see what they asking for.
Yeah.
Okay.
And then match what they give you with what they're asking for and find the formula that,
Right.
that ties all those things together.
Okay. I have one more.
Okay?
It's 5.5.
5.5, that's the next section. Okay? Which number?
Number 5.
Number 5. Okay, this will be on page 137. So let me clear this out of the way. All right, to clear it? Okay, page 137. Is that right? Yeah. Page 137. It's a problem set 5.5, number 5. Find the net force, including its direction, when each force acts in the direction indicated. Well, number 5 has you a 346 newtons to the right. Okay?
I'm thinking you're going to add and subtract these, but I may be...
Yes, that's exactly right. Then you exert a 247 newtons to the left. But add to that another 103 to the left. Left. Okay? So what would you have?
So, let's see.
Add the 2 to the left, and what do you get?
Okay. That's why I got confused there. So the 2 to the left is 350.
350 newtons to the left, and add to that 346 newtons to the right, and what do you wind up with?
So you add both of those?
No, one's to the left and one's to the right.
Oh, they subtracted.
Yes.
Okay.
4 newtons which way?
To the left?
Left, because that was the greater number. Exactly.
Okay. Oh, yeah, that was kind of, I was kind of confused on that, but I think I got it now.
Just think of this as a tug of war, okay? You have bigger siblings or smaller siblings?
I just have one small.
Oh, one smaller sibling. So he brings a friend over, okay? And the friend pulls a 247 to the left, and your sibling pulls 103 to the left, and you're pulling to the right 346. That goes barely gonna move you, but a little bit. 4 newtons. They'll win just barely. Is that what they got in the back?
Yes.
Good. Good deal.
Okay.
All right.
So
Is that
I'll
it?
Go back and look at the
Any more?
questions. Anybody else have
Hey, guess what? Look at this. You timed it perfectly. 6:30 on the nose.
anything? Thank you.
All right. Good deal.